My name is Sachin Joshi. I've been with Dell for a little bit more than 2 years. We are going to talk about SLTS today, which is introducing simplified long-term storage. Um, my aim for this talk is to set the context, uh, explain the big picture, explain the motivation behind why we are doing SLTS, and then go into enough details so that you can start exploring it. So why LTS? So Pravega is a streaming storage, and I have underlined storage because that's the most important word for me. Uh, it's not just a messaging system, it's a storage system. And what that means is durability is fundamental. Once we acknowledge the data is never lost. Uh, Also important is that performance is critical. Flavio earlier explained that we want to have a system where we can ingest data and read the data at low latency, and at the same time, it provides high throughput. Storage efficiency is also important. We do not want to have storage overhead, duplication of data. We want to have a single unified API that works for real-time data, historical data. So it's an excellent choice for Kappa architecture. The fundamental tenet of Pravega is the steering, Flavio talked about it earlier, is automatic, which means that the tiering is done automatically between low latency short-term storage and large capacity external long-term storage. It's going to be space efficient, it's going to be performant, and most importantly, it's going to be completely transparent. The last point which distinguishes Pravega from others is Pravega works with your own external storage. It could be cloud native storage, it could be multi-cloud solution, it could be a specific cloud solution. And we want to meet customers where they are already moving, and those are object stores. It also enables Edge. What Pravega does is it actually converts your choice of external storage into a storage that Pravega can consume, store, and utilize. Um, like I said, LTS, that is long-term storage, is integral part of Pravega storage. Traditionally, we used to do what was called Lambda Architecture. The events were ingested in two separate systems. There was a speed layer, there was a batch layer, there was a duplication of effort and whatnot. The right way, or I would say Pravega way, is you ingest the data once and you have a streaming platform which allows us to read real-time streaming data as well as it serves the data for batch. Again, LTS is integral part of Pravega storage. Traditionally, what we used to do was we used to have lots of applications that have lots of their own way of storing data, and that data was never shared. The Pravega way of doing things is you have a single storage system where all of your data can be stored in a single place. And with the use of Pravega middleware, you can utilize that data. You can use that data in multiple applications. Um, so quick background, the fundamental concept in Pravega is stream. And for this particular talk, the most important concept is the streams are made up of segments. So if you look at the diagram on the right, uh, uh, at the top, we have a stream, which is composed of multiple segments. As the stream progresses, as the time progresses, we might actually add more segments, or we may actually merge multiple segments. Um, the fundamental thing to remember here is stream is composed of segments. And the segments are, the best way to think about segments are just a stream of bytes. And segments can be added at the end, added to at the end, and they can be truncated at the front. Segment store, and I think that the diagram is a little smaller than what I expected, but below there is like a very high level, like 20,000 feet diagram of how the general architecture looks like. So the Pravega client talks with controller and segment store, which are both uh, stateless services. They depend on stateful services, which are Zookeeper for configuration information, Bookkeeper for write-ahead log, and perhaps Cache for uh, the local storage. Um, then these two things they depend on tier one storage, and the segment store automatically tiers data between tier one storage and tier two storage. And by tier two storage, we mean your external uh, long-term storage. It could be object, it could be file system, it could be your own block storage. Um, these are um, these are the storages that segment store will be able to utilize. So the assumption here is the tier one writes are asynchronous. So client actually doesn't directly write to the tier two. The tier one is where the data is ingested, and like Flavio said, the data is staged until it is moved to tier two. The segment is opaque sequence of bytes. As far as segment store is concerned, we do not actually interpret any of the bytes inside a segment. Uh, so with this background, uh, here is the goal. Here is the purpose why we need SLTS. The goal of SLTS is to provide segment abstraction to the upper layers. Like I said, segments are dynamic. They grow at the end, so we keep on appending the data, and they shrink at the head end. So we keep on truncating them at the head end. But otherwise, once written, that sequence of byte is immutable. Segments are the foundational building blocks of everything Pravega. Segments are used everywhere in Pravega. The user streams, the attribute segments, the key value tables, internal Pravega streams, even client state management, and a lot of other things that the Pravega is built on. They use segments to store those data. And all of these upper layers actually assume that this segment abstraction works as expected. And the abstraction is pretty simple. It's a sequence of bytes. You append at the end and truncate at the front. So what are the challenges? One of the biggest challenge with object stores is how do you actually build such a dynamic entity like a segment with immutable objects? So that's one challenge that SLTS needs to solve. The second challenge it needs to solve is how to enforce single writer pattern. When in a distributed system, you always have a partition, you always have a possibility of zombie servers and split brain scenarios. And so how do you actually strongly enforce the single writer pattern? The third challenge is how do you actually implement atomic appends? One of the things that we have to deal when we are dealing with object stores is how do you deal with eventual consistency? And the last problem, which Project that briefly talked about, is during the retention cycle, we have to decide whether to truncate a segment or not, and how do you actually achieve that uh, at the low level. So I'll quickly skip through these problems, and then we'll come back to like what SLTS is, how it solves those problems, and so on and so forth. But let's first quickly go through a couple of problems. So the problem number one is split brain and fencing. The requirement is data is appended atomically, and we have a strong writer pattern, strong single writer pattern. The split brain is any time when we have a partition and two servers legitimately think that they are the owner of given segment and try to write it at the same time. So to avoid data corruption and basically writing garbage, we need to solve that problem. And this can happen because first of all, it's a distributed system. but also because of long GC pauses, right? Um, uh, NFS locks are not NFS locks are problematic. The HDFS appends are atomic, but they are not concurrency safe. The two servers can write and append the same blocks again, and it will actually happily accept those two requests and append duplicate data. AWS has a bigger problem. AWS S3 has eventual consistency. And the current solution, the current implementation actually requires individual providers. Individual providers, by that I mean NFS provider or S3 provider or HDFS provider to solve that problem. So they might actually use some fencing logic, which becomes very complicated because each and every provider has to implement the logic for fencing and handling split brain scenarios uh, based on what their primitives are. And so essentially, instead of solving that problem in one place, we are kind of distributing that problem, and each and every provider has to solve that problem again and again and again. So that's a downside. And it just makes life complicated for uh, people who are implementing those storage providers. The second problem, and I think this is a subtle problem, but a very important one. These days, for the right reason, the object stores are very popular. But for streaming service like Pravega, they come with a problem. And the problem is the objects are supposed to be immutable. And what that means is uh, once written, that same object cannot be modified. You cannot append to that object. You cannot modify a certain range in that object. If you want to uh, modify that object, you have to replace the whole object. So if think about appending data to segments, what that means is we have to read the data, append that data locally, and write that data back. But then we still have to deal with other problems where now we have to deal with um, eventual consistency. The reader, or when you read back that data, are you going to get the older version or a newer version? And so object store actually have this very interesting problem where you are not able to uh, modify the existing objects. And so what that means is we have to find a solution where we have to simulate, or we have to create that abstraction of a nice segment that can be truncated at the front and appended at the end using these immutable objects. So I won't go into all the other challenges. I think those are kind of we'll touch base, but these are the two challenges that SLTS definitely has higher priority. It's a higher priority challenges that SLTS must solve to move forward. So we are kind of defining the scope of SLTS. SLTS again means simplified long-term storage, and the reason for using that simplified word is the first problem, which is until now, we were kind of expecting each and every storage provider to solve the fencing problem, to solve the zombie problem, how to kind of strongly enforce the single writer pattern. In SLTS, our aim is to simplify the API contract for the storage bindings. We eliminate need for complex fencing during failover, and give the freedom to optimize append logic, leverage the storage native merge and concatenation capabilities. SLTS also aspires to provide extensions point for the future, like additional background services like defragmentation, integrity checks, possibility of data compression, encryption, erasure encoding, and all those sort of things. We also can support access control, multiple tiers. Again, That's not what we are doing in this particular 0.9 or 0.10 milestone, but it's an extension point for the future. What is out of scope for SLTS? We are still requiring Pravega to read data from Pravega. We are not talking about exporting and importing pre-existing data in other formats. For example, Avro, multiple tiers, at least for short term, it's out of scope. So with that background, let me quickly go into uh, so we talked about what SLTS is trying to solve. Now we are going to deal a little bit about, talk a little bit about like how SLTS solves that problem. On the left, you have segment store current architecture, and the right, we have a new design. So as you can see, uh, there is a cache, and that cache actually calls two components called storage reader and storage writer. The older storage system was called async storage. It actually called into something called rolling storage. And then finally, at the bottom layer, there was these things called sync storages, which is either HDFS, NFS, or extended S3. With SLTS, what we are doing is two things. First of all, we are introducing a metadata table store, which stores the data about chunks. It stores the data about storage layout. And we are also introducing storage optimizer services, which are garbage collection, defragmentation. The main change is the the async storage is replaced by chunked segment storage, which talks with metadata, the table store, and which talks with chunk storages. The chunk storages are the new API that we are exposing so that, and I will talk about that in a minute, so that they can actually, the storage providers can implement a simplified API. Um, so the chunks segment storage is the component that manages the underlying storage and talks to the storage providers using chunk storage API. So in short, what SLTS is a unified chunk management layer. So what is segment? What is chunk? Chunk is a unit of storage. You can think of it as a chunk as an actual thing that gets stored on your external tier 2 storage. If it's a file, then if it is a file NFS-like storage, then it's a file. If it's an object storage, then it's an object. So it's the leaf node in the storage hierarchy, um, and it's a unit of storage. It can support append. But the only expectation we have is if it supports append, the only requirement is that it has to support append-only writes, right? Sorry, the right way to say it, as long as it supports append-only writes, we are able to utilize your storage. The unified chunk management layer enforces a strong single writer pattern with this particular assumption that is enforced everywhere, is the chunks can only be written by the instance that created them. That eliminates the problem of two different server instances trying to modify the same underlying file or object. So that's one of the tenets of the design. The second is immutable. The chunks are immutable. Once they become inactive, they're considered sealed. They will not be modified. The chunk names themselves are arbitrary, but the only requirement is that must be globally unique. Like I explained before, the segment is made from multiple chunks. You can think conceptually. There is a diagram at the right bottom. You can think of it as a segment is segment is made up of two types of records. A segment header has information about segment itself, and then individual chunks, you can think of them as metadata records that point to the underlying files or objects. And conceptually, you can think of a segment as a linked list of chunks. A new chunk is added whenever a new segment is written for the first time, obviously. After failover, I just explained that we enforce this strong single writer pattern, or the underlying file or object reaches its limit. And the fourth is when underlying storage does not provide safe append semantics. And so in case of failures, we might actually decide that it's more safe to actually start a new chunk than to figure out the consistency of the existing chunk. So chunk segment storage is the component which we like to call SLTS, Simplified Long Term Storage. The key point of this design is we are separating data from the metadata. The metadata about the chunk is stored in a separate table-based metadata store. Metadata is stored using a bookkeeper-based table. It's stored as key value pairs. The table is pinned to the container. The metadata updates are atomic, which means all the keys change at once or none at all. That simplifies the error handling in a major way. The metadata updates need to be efficient. They need to be infrequent. As far as possible, they need to be lazily writing data. They need to be cached extensively. So we are using a write-through cache for read performance. Like I explained before, the metadata records offer a point of extensibility. We can have access control list. We can have CRC-based checksums and whatnot. The requirement for metadata store are simple. They need to provide optimistic version-based concurrency. What that means is, in theory, we can use Zookeeper. We can use any key value store that provides version-based optimistic concurrency. The API that now we expect the individual storage provider to implement, it's vastly simplified. All the complexity of fencing is removed. It's concentrated in SLTS. It handles all the failure scenarios. It handles all the fencing logic. The API that we have for chunk storage is essentially a very simple CRUDL API, which you need to be able to create object, read object, open the object for read or write, delete the object, list the object. You get the attributes like size of the object. Optionally, you can merge two objects or truncate the object at the end, make it read only. Again, the API is very simple. All the complexity is gone. So in short, I mean, I went through a lot of slides, talk about a lot of things, but what I want us to remember at the end is there is a certain reason why we wanted to do SLTS. There were certain problems we need to solve with SLTS. And here are the advantages of SLTS. From a technical point of view, we are clearly separating the responsibility. The storage providers must only support like just the simple CRUDL operations. The SLTS actually takes the responsibility of implementing single writer pattern, atomic appends, dealing with eventual consistency, dealing with creating segments out of immutable objects. Again, another advantage of SLTS is we are extensively using asynchronous programming model. And what that means is we have increased concurrency. We have higher degree of thread utilization, higher degree of parallelism, higher kind of read and write throughput, and also lower latency. Uh, One of the core reasons why we are doing SLTS is also robust failure handling. So all that is implemented by SLTS. The actual API that the storage providers have to implement is vastly simplified. From the functional point of view, the biggest advantage of SLTS is now we have a plugin model which enables third-party storage adapters uh, to implement storage adapters for Pravega for wide varieties of systems. In near future, we will have a SDK and a test suite so that you can actually test your implementation against a given test suite. Um, but one of the things is the batteries are included. Pravega does come with built-in adapters for NFS, HDFS, ECS, which has extended S3 storage. And in near future, we will have a S3 adapter for Pravega. Um, it also comes, it also uses its own built-in metadata store. So we already have Pravega table store, and we use it internally, and it's fine-tuned for SLTS usage pattern. So out of box with SLTS, you can start using NFS, you can start using HDFS, you can start using extended S3. In near future, you will also have S3. Again, it goes without saying that once we have the plugin model, there could be a community owned or community developed storage providers, for example, for Azure, for GCP, for Swift, you know, and there are many other storage options available today, and we can create an ecosystem of storage providers. So let me conclude by giving a sneak preview of the roadmap. Again, this is tentative. We are not committing to any dates here. SLTS is experimental feature. Things might change. It's a new feature, so we might actually shuffle, what goes in what release. But here is a general timeline. We had an alpha release of SLTS in 0.8. 0.9 is where we are introducing SLTS. It's experimental. We have initial bindings for file system. We have for HDFS, for ECS. 9.1 is more like a service release where we are fixing stability issues. We are fixing other bugs. Next release, we are hoping that it's a stable release. And by stable, I mean the API is no more experimental. It's going to stay the same. It will be supported long term. The metadata written on the LTS will be supported. It will be backward compatible, forward compatible for the future. In next release, we will, like I said, the plan is to have S3 binding for AWS. We'll also have admin and diagnostic tools. We do plan to have a proper SLTS SDK for and a test suite, and then we'll have some migration tools. In future, our goal is to make SLTS the Pravega default Pravega LTS subsystem. So that's a kind of a brief overview of what SLTS is. I think I am personally pretty excited about it, and I think it will be a good idea for you to take a look. And I'm looking forward to your feedback. Quick slide on how to enable SLTS today. So there is a config setting. You just kind of say Pravega service dot storage dot layout is equal to chunk storage, and that will actually enable SLTS. Please keep in mind that SLTS, because it changes the way data is laid out on the LTS, it's not backward compatible today. So it only works for freshly installed systems. Um, but if you want to experiment, this is the setting you have to set. References, the design document is available on Pravega Wiki. It's a PDP 34 simplified tier 2. There is a Slack channel, Pravega LTS, in our Pravega Slack. So yeah, that's all I have for today. Please please let me know what you think. I'm looking forward to your feedback, and I'm definitely excited about SLTS.